So what if I told you there's a 2,500-year-old formula that's still being used, right now, to build skyscrapers and even design video games? Well, today we are breaking down one of the most fundamental tools in all of geometry. We're going to build a complete toolkit for understanding and using the Pythagorean Theorem, all based on a really cool one-on-one tutoring session.
Okay, let's just dive right in. The source material for this whole explainer gets straight to the point with this opener. It perfectly sets the stage for what we're about to do. Unlock the secrets of this powerful formula one step at a time.
You know, before we even get to the famous formula, we have to start with a question. And this is the first major problem the theorem helps us solve. Say you're given 3 side lengths. How can you know for sure if they form a perfect right triangle? To answer that question, we're going to need a very specific tool. It's a simple but incredibly powerful equation that's been around for thousands of years, discovered by different cultures all over the world. And here it is. A squared plus b squared equals c squared. This little formula right here is the key to everything. It describes this special relationship that only exists between the 3 sides of a right triangle.
Now you're probably wondering, what are A, B, and C? Well, this slide breaks it down perfectly. A and B are the 2 shorter sides. They're called the legs. You can swap them, it doesn't matter. But C is the special one. C is always the hypotenuse. And the tutor in our source material really drills this in. It is always the single longest side of the triangle. Finding C first is the most important step, for sure.
All right, so we've got our formula, and we know our A, B, and C. Let's put this thing to the test. We're going to use the theorem to see if a set of sides can actually form a right triangle.
Okay, here's our first challenge from the session. We've got a triangle with sides 6, 8, and 9. So first things first, what's C? Well, since C is always the longest side, it's got to be 9. That means A and B are 6 and 8.
Now, let's walk through the math. We just plug our numbers into the formula. So, 6 squared plus 8 squared equals 9 squared. Okay, let's solve those squares. That gives us 36 plus 64 equals 81. And then we add the legs together, which gives us 100 on one side and 81 on the other.
The last step is just to compare. And 100 does not equal 81. Not even close. The 2 sides of the equation just don't balance. So here's the crucial takeaway. Because the equation isn't true, the theorem doesn't work. This means that this set of sides, 6, 8, and 9, absolutely cannot form a right triangle. And that's how we know for sure. It's like a truth detector for triangles. Okay, let's try another one real quick. A triangle with sides 5, 12, and 13. Here, 13 is the longest side, so that's our C. Let's plug them in. 5 squared plus 12 squared should equal 13 squared. Well, that's 25 plus 144, which is 169. And guess what? 13 squared is also 169. So we get 169 equals 169. It's a perfect match. Yes, this is definitely a right triangle. So, testing triangles is one of the theorem's superpowers. But its other superpower is maybe even more useful, finding a missing piece of the puzzle. This is where the theorem goes from being a test to a true problem solver. In the tutoring session, this is actually where the student dash kind of hits a wall. We have a triangle that we know is a right triangle. We know its legs are 6 and 3, but we have no idea what the length of the hypotenuse, C, is.
So we start the same way. We plug in what we know. 6 squared plus 3 squared equals C squared. That simplifies down to 36 plus 9 equals C squared, which means 45 equals C squared. And this is the moment of confusion. We're so close, but 45 isn't the answer.
So how in the world do we get from C squared to just plain C? Well, it turns out we need one more operation, basically the opposite of squaring a number. This is the exact question that stumps so many people when they first learn this stuff. It's a great question. We found what C squared is, but that's not the length of the side. So, how do we isolate C? And the answer is the square root. Seriously, just think of it as the undo button for a square. To get C all by itself, we have to take the square root of both sides of the equation. So C is simply equal to the square root of 45. And this is that aha moment. You can practically hear the light bulb go on over the student's head. After hearing the explanation, he immediately realizes the next step. He knows he just needs a calculator, like Desmos, to finish it off. It's that moment where the whole process just clicks. And when you punch the square root of 45 into a calculator, you get about 6.7.
And there it is. The missing length of the hypotenuse, our C, is 6.7. Problem solved.
And just like that, we have a complete toolkit. We've seen how to use this one theorem for 2 different, really practical jobs.
So, let's do a quick recap. What are the key takeaways here? First, it all starts with the formula. A squared plus B squared equals C squared. The absolute number 1 rule is that C, the hypotenuse, is always the longest side. You can use this formula for 2 things, to test if a triangle is a right triangle or to find a missing side. And don't forget, that final secret weapon? To find the actual length of a side, you often have to use the square root.
Look, this theorem isn't just for a math class. It's used in construction every day to make sure corners are perfectly square. It's used in navigation to find the shortest distance between 2 points. It's even in the code for video games. So the final question is, now that you have this elegant and powerful tool, what real-world problems could you go out and solve with it?